Dear students, today we will discuss about the frequency spectrum of FM wave, and also we will discuss about bandwidth and power of the FM wave. We have gone through the frequency modulation. In the case of frequency modulation, the frequency of the carrier is varied in accordance with the amplitude of the modulating signal. So the change will occur for the frequency of the carrier wave in the case of frequency modulation. So in the case of frequency modulation, we can represent the FM wave by using the equation EFM, where EFM is the instantaneous value of the frequency modulated wave. That will be equal to EC into sine omega CT plus MF into sine omega M into T, where EC is the amplitude of the carrier signal and omega C is the carrier frequency, that is angular frequency for the carrier. MF is the modulation index and omega M is the modulating signal frequency, that is angular frequency of the modulating signal. So in the case of, you can see here the carrier wave frequency component is modified and it will contains the carrier frequency and also the modulating frequency, that is this equation's meaning. So in order to find the frequency, different frequency components present in the FM wave, we have to use Bessel function equation. So by using Bessel function, we can expand this term. So we can write EFM. See, you can see here, instantaneous value of the FM wave EFM will be equal to, we can write it as A into J0 MF sin omega CT plus J1 MF into sin omega C plus omega M into T minus sin omega C minus omega M into T plus J2 MF into sin omega C plus 2 omega M into T plus sin omega C minus 2 omega M into T plus etc. So here you can see that A is the magnitude and J0, J1, J2 etc. are the Bessel coefficient and MF is the modulation index, and first component is carrier component omega C, that will correspond to a frequency Fc, and second component is omega C plus omega M and omega C minus omega M. This represents the upper sideband and this represents the lower sideband, that will be situating next to omega C or Fc carrier frequency. It will be situating left to the this frequency will be situating left to the carrier frequency. Similarly, next component is omega C plus 2 omega M, that will be situating 2 FM far away from the central frequency Fc, and this is also situating 2 FM far away from the central frequency. So from this equation you can find that FM will contain infinite number of frequency components. Okay, and all frequency components are situating right and left to the central frequency Fc. So in this expansion, FM wave contains carrier frequency Fc, that is the central frequency, and the infinite number of sideband frequencies. Okay. So the frequency separation between the successive sidebands is, you can see in the equation, it is FM. That means all sidebands are symmetric around the carrier frequency. So the central frequency is Fc and first sideband is FM from FM, that is right to this Fc, and second one is left to Fc. Similarly, next sideband is 2 FM from far away from this Fc, and other one is 2 FM far away from the Fc, that is situating left. So each of the sidebands are separated by a frequency of FM, right? FM and 2FM are separated by FM. Here also FM and 2FM are separated by FM. And its amplitude is given by Fc has an amplitude EC into J0 MF. Similarly, FM, the first frequency component has the amplitude EC into J1 of MF. From the diagram it is clear that the amplitude decreases as the number of sideband increases. So theoretically we can say that since it contains infinite number of sidebands, its bandwidth is infinity. Okay. So theoretically the bandwidth of the FM wave is infinity, but practically it is calculated based on how many sidebands have a significant amplitude. So you can see in the spectrum there are infinite number of sidebands, that is upper sideband and lower sideband are there, infinite number of sidebands are there. So which of the sidebands have finite amplitude, those sidebands will constitute the bandwidth. Okay, so we can say that if there is n number of sidebands which is having finite or significant amplitude, then the bandwidth is obtained by the relation bandwidth will be equal to 2 times n into fm. That is, bandwidth is equal to, in the case of amplitude modulation, you may 2 fm is the amplitude, but here it consists of infinite number of sidebands. So practically it has bandwidth of infinity, but theoretically we can say that theoretically it has an infinite bandwidth, but practically we can say that based on the number of sidebands, its bandwidth is 2n into fm, where n is the number of sidebands. So when modulation index increases, the bandwidth increases due to the increase in the sideband. So when modulation index is increasing, then the number of sidebands will increasing. So the bandwidth will be increasing. So we can also define the bandwidth of the FM by using the Carson's rule. Carson's rule states that bandwidth of the FM wave is twice the sum of the deviation and highest modulating frequency. So bandwidth of FM will be equal to 2 times maximum frequency deviation plus maximum modulating frequency. So bandwidth of FM will be written in terms of equation as 2 into delta F plus FM, where delta F is the deviation, maximum frequency deviation, and FM is the modulating frequency, that is the maximum modulating frequency. So bandwidth we can written in terms of 2 into delta F plus FM. So this equation will be useful for doing problems. So theoretical equation for the bandwidth is 2n into FM. Next, let us calculate the average power of an FM wave. See, the peak voltage of spectrum components in the case of FM is given by En max is equal to Jn of beta into Ec max. See, here you can see, here this one is amplitude and it is given by Ec, which is a carrier frequency, into J0. J0 means it is a Bessel function, and MF. MF is the frequency modulation or modulation index. So we can write the peak voltage of the spectral components is given by Jn of beta into Ec max. Here it is the Bessel function coefficient, and therefore we can write the RMS value of the voltage here as RMS value of voltage, that is given as En. For the nth sideband, the RMS value of the voltage En will be is equal to Jn beta into Ec. Here also this is the Bessel coefficient. And for the fixed load resistor R, the average power of any spectral component is given by, we know that power is equal to voltage into current or voltage square by resistance. So we can write in terms of the RMS value of the voltage, the power will be equal to Pn equal to En square by R, where Pn is the power associated with the nth sideband and En square is the RMS value of the voltage square. So the total average power in the case of FM will contains the sum of all spectral components. See, here it represents the nth sideband. In the case of FM, there will be large number of sidebands. So the total average power is the sum of all spectral components of the FM. So it includes the carrier and also the pair of sidebands. So for each side frequency or sidebands, there will be two powers, that is P0 is the power for the carrier wave and 2P1 means the power for the first sideband. 2P2 is the power associated with the second sidebands. So first sideband means it contains upper sideband and lower sideband. That is why we are writing 2 times P1. 2 times P2 means it is a power associated with the second sideband. It will also contain upper sideband and lower sideband. That is why we are written as 2 times P2. So we can write in terms of RMS voltage, we can write the power equation as PT will be is equal to, instead of P0 we can write E0 square divided by R. Similarly for P1, P2, etc. we can write it as E1 square by R, E2 square by R. R is a constant value, so we can take it outside. So we will get E0 square by R plus 2 by R into E1 square plus E2 square plus etc. So in terms of the unmodulated carrier and Bessel function quotient, we can write for E0. E0 will be equal to Pt equal to EC square into J0 square beta by R. See, we have written the RMS value of the voltage as Jn of beta into EC. That is why we are writing, instead of E0 square, we are writing EC square into J0 square beta. Similarly, for E1 square, we can write EC square into J1 square of beta. For E2 square, we can write EC square into J2 square of beta. Here, EC square are common, so that is why we are writing it outside. Here EC square by R are common, so we can take it commonly outside. So this will give J0 square beta here plus 2 here into J1 square beta, J2 square beta, etc. And this summation will give a value of 1 based on the property of the Bessel function. So we will write Pt equal to Pc square into 1 divided by Pt is equal to Pc square into 1. So we know that carrier power Pc square will be equal to En square by R. So we can write a Pc square is equal to Ec square by R. That is a unmodulated carrier power. So we will get the total power will be equal to Ec square, total power Ec square by R. So RMS value of the total power P total equal to carrier power, that will be equal to Ec square by R. If we are calculating the average power, instead of Ec RMS value, we can write EC by root 2 whole square by R. So we will get a total average power equal to EC square divided by 2R. So that's all about this topic. Thank you.